This video is going to focus on the central limit theorem and confidence intervals. Specifically, we're going to look at three things. First, how is the central limit used to find the probability of an event? How are confidence intervals used to estimate the mean when the population standard deviation is known? And lastly, how are confidence intervals used to estimate the mean when the margin of error is known? So a couple of things that we know. We know that as a distribution gets larger, the sample means tend to be closer to normal. So according to the central limit theorem, a population can have any distribution. It doesn't have to be normal, as long as the number of pieces of data in that distribution is more than 30. So when n is greater than 30, the distribution of sample means can be approximated by a normal distribution. 30 is the magical number to ensure that that can happen. So there's a couple of checks that you need to do. When you're using a mean from a sample, you need to make sure that the normal distribution can be used, and you do that by checking to make sure that the number of data values is greater than 30. Are you using a normal distribution with a single value x or the mean x bar of a sample of n values? If you're using a single value, like we were doing in previous problems, you'll stick to the formula x minus mu over sigma. If you're using a mean from a sample of values, you're going to have to use the formula you see below. You're going to have to divide sigma by the square root of n. So let's look at how those two different scenarios play out within a single problem. When designing an elevator, weight's an important consideration. So the table below shows the values of recent parameters. If an elevator is loaded to capacity of 2,500 pounds with 16 males, the mean weight of a passenger is 156.25 pounds. Find the probability that one randomly selected adult male has a weight greater than 156.25 pounds. So in this case, we have one single value. So we're going to use that z is equal to x minus mu over sigma. We're going to take the 156.25, we're going to subtract 182.9, and we'll divide that by 40.8 in order to get z. When we simplify that, we end up with z is equal to negative 0.65. So then we'll go ahead and use our table of values or use our graphing calculator to find that probability. In the second problem, though, we're trying to find the probability that a sample of 16 randomly selected adult males has a weight greater than 156.25. So in this case, we need to use the central limit theorem because we're dealing with the mean of a sample of 16 and not an individual male. So in this case, to find z, we're going to take x bar minus the mu of x bar and divide it by sigma over the square root of n. So we know that x bar is 156.25, and again, we'll subtract 182.9. So that piece doesn't look any different. But now, when we go to divide, we're going to divide it by 40.8 over the square root of 16. So in this case, we get that z is equal to negative 2.61. So again, at this point, you'll use the table to find the probability that z is less than negative 2.61. And when you look that up in the table, you'll get 0.0045. So you can see that there's two different processes. One, if it's a single value, and the other, if it's sample means that are being used. Confidence intervals can help us by estimating a population mean. We can estimate a population mean within a certain amount of confidence by creating an interval that we know then that the mean will fall in between. So there's some requirements. The sample either has to be a simple random sample, or the population has to be normally distributed, or n has to be greater than 30. One of those requirements has to be met. To get the interval then, you're going to do x bar minus e and x bar plus e. So how do you find e? To find E, which we call the margin of error, you're going to take a critical value, which we'll look at on the next slide, and multiply it by sigma over the square root of n. X bar in this case is considered what we call a point estimate. It's our point estimate for our population mean. So the critical values that we're going to use in this particular section are given here on this slide. And this is just something that I would expect you to access. If I'm looking for a 90% confidence interval, then I know my critical value is going to be 1.645. For 95%, it's 1.96, and for 99%, it's going to be 2.575. So let's look at how we use all of this. Suppose 12 highway speeds of drivers are obtained, and we know that it's approximately normal. And so you can see those 12 highway speeds listed there. Construct a 95% confidence interval estimate of the population mean by assuming that sigma is 4.1. Now, n here is not greater than 30, but we're going to pretend like this is absolutely positively normal. So that's going to make our job a little bit easier. So if I want a 95% confidence interval, I'm going to look back to see what that critical value is. That critical value is going to be 1.96. We would take that 1.96 and multiply it by 4.1 divided by the square root of 12. And that's going to give us our margin of error that we will add and subtract to the point estimate. If we go ahead and find x bar for those values, we can determine that x bar for these 12 highway speeds is 60.7. So then we will go and we'll add the error that we found to it, and we'll also subtract the error that we found from it, and that will give us our confidence interval. From those two numbers, we can be 95% confident that any highway speed of any driver would fall between those two values. We will focus a lot on the interpretation of the values, even more so than finding the values themselves. Now, I'm not going to expect you each time to go through that process. You can use your graphing calculator and go to Stat, but this time you're going to arrow over to the word Tests, and you're going to select Z interval. All the intervals that we do, we're going to assume that sigma is known. You can either enter the actual data, so you would click on Data, or if you're given a summary, go ahead and enter the stats that you're given. Set the confidence level to what you need, whether it's 0.9, 0.95, or 0.99, and then hit Calculate. You'll be given two numbers separated by a comma, and those two numbers will be the lower and upper limit for your confidence interval. So suppose you have a sample of 106 body temperatures, and they have a mean of 98.20 degrees Fahrenheit and a standard deviation of 0.62 degrees Fahrenheit. Construct a 95% confidence interval estimate of the mean body temperature for the entire population. I want you to practice doing this on your graphing calculator. So I want you to go to Stat, Tests, Z interval, and I want you to enter the statistics that you're given here and calculate the 95% confidence interval. And then I want you to enter that answer to the screen to the right. So let's do it by hand and check to see if you got the same answer. For a 95% confidence interval, we know that the critical value is going to be 1.96. So I'm going to take that 1.96 and multiply it by 0.62 over the square root of 106. That's going to give you your margin of error. When you do that, you get a margin of error of 0.11803. So we're going to add that to the 98.20 and subtract it from the 98.20. So when we add it, we end up with 98.32, and when we subtract it, we end up with 98.08. So this means that we can be 95% confident that all body temperatures are between 98.08 and 98.32. So what does that result suggest about the belief that 98.6 is the mean body temperature? Well, that mean body temperature isn't true for 95% of people. So to summarize, to the screen to the right there's two questions. What does n have to be for the central limit theorem to hold? And what do you have to check before constructing a confidence interval? What do you have to make sure of? Now you can go back to your homework assignment for this week and fill in the missing problems that you weren't able to do after the first video.